Alright, in this video we'll be going through the 2019 Mechanics Exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video to see how I go about getting the answer. Alright, so Ellie and Chris are rollerblading, assume there is no friction. The system of Ellie and Chris can be considered an isolated system in the horizontal direction. State a relevant physical quantity that is conserved during a collision between Chris and Ellie. So there are actually three in this case, but again, you only need to describe one, so if you've only described one, that's all good. So the first one that we can write down is momentum, and more specifically linear momentum, okay? And the second one being the velocity of the center of mass of the system, okay? And the third one being the total energy of the system. Okay, again, you only need to write one of these, okay? At one instant, Ellie stops and Chris collides with her. They move off at right angles to each other as shown in the diagram below. Show that Ellie's speed right after the collision is 1.71 meters per second. Okay, so as we know, momentum is conserved, and so the momentum initially must equal to the momentum finally, okay? And as we know, momentum is a vector, so we must use vector triangles to solve this equation. We can see initially only Chris is moving and Ellie is stationary, right? We can see the velocity is 0. And so our initial momentum is only going to be the momentum of Chris. And as we know, momentum is equal to mass times velocity, and so the momentum initially is going to be equal to Chris's mass, which is 60 kgs, times his velocity, which is 1.8, and this gives an initial momentum of 108 kg meters per second, okay? And as we can see right here, Chris moves up this way, so his momentum vector is like this, and Ellie moves down at this direction, and so her momentum vector is like that, okay? And we know that there is a right angle over here, as seen over there, okay? We can calculate Chris's momentum after the collision, and so that is, again, P is equal to mv. His mass has not changed, so it's still 60 kgs, and now his velocity is 1.1, and this gives a momentum afterwards of 66 kg meters per second, okay? And what we want to find is Ellie's momentum afterwards, because we have no information on that, right? So we want to find Ellie's momentum afterwards, okay? Luckily for us, this is a right angle triangle, and so we can use our Pythagoras, okay? Therefore, P Ellie is equal to square root 108 squared minus 66 squared, okay? And therefore we have P Ellie as 6 square root 203, or you could write it as 85.49, okay? kg meters squared, okay? And therefore, again, as P Ellie is equal to her mass times her velocity, and what we are trying to find is her velocity, right? 1.71 meters per second. And so her velocity is equal to her momentum all over her mass. She has a mass of 50 kgs, okay? So now plugging in our numbers, using this for whole value purposes, okay? And this gives a velocity of 1.71 meters per second. There we go. To save himself from falling, Chris sees a horizontal bar and grabs it. He then swings on the bar in a vertical circle. Chris's motion can be simplified by analyzing the motion of his center of mass, which is 0.7 meters away from the bar. Calculate the minimum speed Chris's center of mass would need to have at the top of the vertical circle in order to swing up and over the bar. Assume he continues in a circular path. So clearly this is a question of minimum speed. If you have not covered minimum speed, I go through it in my vertical circles video on my mechanics playlist, so you can go check that out. But as we know, for minimum speed, our FC is equal to our weight force, and therefore mv squared all over r is equal to mg. We can cancel out our masses, and we get v squared all over r is equal to g. Rearranging for our velocity, we get v squared is equal to gr, and therefore we can say that square root gr is equal to our velocity. And therefore now we can just plug in our numbers. Our velocity is equal to square root 9.81 times our radius, which we are given here as 0.7. And this gives a velocity of 2.62 meters per second. There we go. Describe and explain the size and direction of the tension and weight forces at the bottom and top positions, assuming Chris is swinging at the top at minimum speed. Include force labels on the diagram below to support your answer. So at the top, as stated in the previous question, for minimum speed, all the centripetal force is provided by the weight force, okay? And so at the top, there will be no tension force, so at the top, tension force is equal to 0. and therefore he will purely only have a weight force, so there will be no tension vector. However, at the bottom, he will still obviously have a weight force because he still has mass, okay? But as we know, for circular motion, there must be a net force to provide a centripetal force in order for it to go into a circle, right? However, this centripetal force must act towards the center of the circle. And as we can see, our weight force is acting in the opposite direction, towards the outside of the circle. And so therefore, we must have a tension force present, okay? And this tension force must be greater than the weight force, okay? The reason for this is because, again, our FC is a net force, okay? And therefore, as we know, in order for there to be a net force, the forces can't be balanced. So if our tension force and weight force were balanced, that means there will be no net force and therefore no FC. And as I previously said, our tension force must provide our centripetal force, and therefore it must be larger in order for there to be a net force present, okay? So what we can say in our answer is that our weight force is constant and acts downwards at all times. At the bottom, the tension force, so Ft, is much larger than our weight force, okay? And this is to provide Fc, okay, a centripetal force. At the top, our Fc is provided entirely by our weight force, and this is due to minimum speed. Therefore, our F tension is equal to 0. All right, and as always, you can't just write this in and get excellence. You need to write coherent sentences, not just bullet points, and so you can write that in yourself. 3 children are playing on a merry-go-round with a rotational inertia of 271 kg meters squared. Once the children get the merry-go-round spinning, they stand evenly spaced on the outer edge. Each child has a mass of 28 kgs, and the merry-go-round has a radius of 2.1 meters. Assuming the rotational inertia of the child's mass on the edge of the disk is given by I is equal to mr squared, show that the rotational inertia of the system is 641 kg meters squared. So we want the rotational inertia of the system, and so therefore the entire system consists of the merry-go-round, so merry-go-round, mgr, plus the rotational inertia of the children, ic, okay? So we are given the rotational inertia of the merry-go-round as 271, plus the rotational inertia of the children, and that's equal to 3 times the mass of a child, which is 28 kgs, times the radius, which was given as 2.1 meters, and that's all squared, okay? And this gives a total rotational inertia of the system as 641.44, and if we round down, we get 641 kg meters squared. There we go. The total energy of the system is 388 joules. Show that the angular velocity of the system is 1.1 radians per second. So we know our rotational kinetic energy is equal to half I omega squared. We just found the total rotational inertia of the system, okay? And we are trying to find the angular velocity, and we are given the total energy of the system, okay? So now it's just a simple case of rearranging. We get 2ek all over our rotational inertia is equal to our omega, and we can square the entire thing. And so we get square root 2 times 388 all over 641 is equal to our angular velocity, and that's given as 1.1 radians per second. There we go. And second part of the same question, it wants us to find the linear velocity of one child, okay? We know that our velocity is equal to the angular velocity times our radius, and so therefore our angular velocity, which we just found, was 1.1 times our radius, which is 2.1, and this gives a velocity of 2.31 meters per second. There we go. And as you can see, that is the exact number we're trying to find. One child drags her foot on the ground to bring the merry-go-round to a stop in 2.8 seconds. Calculate the amount of torque produced by the foot. Okay, so we know our torque is equal to I alpha. Okay, once again, we already know the rotational inertia of our system, which was 641.44 kg meters squared. Okay, we are trying to find the torque. However, we do not know our angular acceleration. What we do know is that angular acceleration is equal to the change in angular velocity over time. We are given our time value, and we also know that the merry-go-round used to be spinning at 1.1 radians per second, and we are bringing the merry-go-round to a complete stop. So our omega initially was equal to 1.1 radians per second, and our omega finally is equal to 0 radians per second. Okay? And so therefore, plugging this into here, we get our alpha is equal to omega finally, which is 0, minus 1.1, which is our omega initially, all over time, which is given as 2.8 seconds. And this gives an angular deceleration as negative 11 all over 28, or you could say negative 0.392 radians per second per second. All right, now that we have our alpha, we can simply plug it back into this equation right here. Again, our rotational inertia is given as 641.44 times 11 all over 28. Again, using the fraction for whole value purposes, and also not including the negative because we do not care about the direction in this case. We just want to know the torque produced, so that's just the magnitude, okay? The negative in this scenario is just telling us it's deceleration, okay? And so this gives a torque value of 251.99, and therefore that's the same as 252 Newton meters. There we go. Now, if you plugged in negative 11 all over 28 and got an answer of negative 252 Newton meters, on the marking schedule, it doesn't mark it as correct, but I assume you would be correct in this case, but it doesn't have it on the marking schedule, so don't quote me on that. But I assume you would be marked correct. The children get the merry-go-round spinning once again at a constant angular speed. Then each child moves inwards towards the center of the merry-go-round. Use physics principles to explain the effect on the rotational energy of the system. Alright, as our rotational inertia is directly proportional to mr squared. As each child moves inwards to the center of the merry-go-round, the effective radius of the merry-go-round is going to decrease. Once again, if you don't understand what effective radius is, I go through it in my rotational motion video on my mechanics playlist, and so you can go check that out. So our effective radius is going to decrease, and therefore as our mass of the system does not change, our rotational inertia is also going to decrease. As our angular momentum is conserved and therefore is constant, and our angular momentum is equal to I omega, if our rotational inertia has decreased, therefore our angular velocity must increase. And therefore, it wants us to comment on the rotational energy of the system. We know our EK rotational is equal to half I omega squared. Even though our rotational inertia has decreased, because our angular velocity is squared and our angular velocity is increased, it's going to increase by a higher amount than our rotational inertia is going to decrease, and so therefore our rotational kinetic energy is going to have a net increase. And so you can write that in words. J is enjoying a swing at the playground. The period of one oscillation is 2.4 seconds, and J maintains a constant amplitude of 0.31 meters by swinging her legs back and forth to replace the energy lost due to friction. The mass of the system, which is J and the swing, is 70 kgs. J's motion can be considered simple harmonic motion. Calculate the maximum velocity of J and the swing. So we know that V max is equal to A omega. If I am not mistaken, this equation is not given to you on your formula sheet, but in my reference circle video, I go through how we can derive this expression, okay? And so therefore, our velocity max is equal to the amplitude, which is 0.31, times her angular velocity, which is not given, but we know that angular velocity is equal to 2 pi all over the period, and we are given a period of 2.4 seconds, so therefore 2 pi all over 2.4. And this gives a max velocity of 0.812 meters per second. There we go. Use a reference circle or other method to determine how much time J's displacement is greater than 0.2 meters from the equilibrium over one period. Alright, so we have a reference circle right here, like so. And we know the max amplitude, which is the radius in our case, is going to be equal to 0.31 meters, okay? So what we want to find is how much time are we greater than 0.2 meters from the equilibrium position, okay? And so what we're trying to find is how much time are we within, let's say, like here, within these regions of the reference circle, okay? So as we know, we're starting at the equilibrium position, and we can draw our phasor down here, okay? Let me get this distance right here. This is theta, okay? We can draw out that right angled triangle, theta over here. We know that this is 0.31 and this is 0.2. And so therefore, theta is equal to the inverse sine, 0.2 all over 0.31. And this gives a angle of 0.701 radians, okay? Again, with reference circle, always work in radians. And we know our theta is equal to omega t, and therefore our time is equal to theta all over our omega. We remember our omega was 2 pi all over 2.4. Remember, 2.4 was our period, and so therefore our time is equal to 0.701, and remember, use the whole value for your angle, okay? This is just a rounded value, all over 2 pi divided by 2.4, and this gives a time of 0.278 seconds. Okay, so now what is this time? this time is the amount of time it takes from us to come from the equilibrium position to 0.2 meters from the equilibrium position. So the amount of time it takes to go from here to here. Okay? Now that time is the exact same time to come from here to here, and from here to here, and also from here to here. And so what we can do is times that value by 4, okay? And we get a new t value of 1.07 seconds, okay? However, like I said at the start, we are trying to find the time where J is over 0.2 meters from the equilibrium position, and so we're trying to find these regions right here, okay? However, we found these regions. So what we can do is take the period and minus our time, okay? So we get 2.4 minus 1.07, and we get 1.33 seconds. There we go. Now, how I got 1.33 seconds is because this, again, is not the whole value. The whole value for that is like 1.0714071888, okay? So I just wrote down the rounded value, okay? And so 1.33 is our final answer. That is how long J spends above 0.2 from the equilibrium position. Now, remember, that is not the only way to solve it. You could have just gone straight to here. You could have found this angle right here and done the exact same thing. I just decided to do that way, okay? It's not the only way to solve it. So if you solved it another way, completely fine. J stops swinging her legs when the swing is at maximum displacement. On the grid below, sketch a graph of a displacement on the next 3 periods. Include values for time and the initial displacement at t is equal to 0. Okay, so we can split this off into 3 sections, like so, okay? T1, T2, T3, okay? We start at max displacement right here, and we found at the start that our max displacement was 0.310 meters, and so therefore on the negative side, that's going to be negative 0.310 meters, okay? Now, this exam is nice. We are given a grid. I hope you're given a grid for your exam. Sometimes they don't, and it's just really annoying. But because now we're given a grid, this makes it very, very easy. What I like to do is just minus by 1 square every single time. So we are over here, and when we come down, we can end right about here, okay? So that's 1 square up. And then when we come over here, we instead go 2 squares down, like so. And then we come over here, and we go 1 square up from here. And then we go 2 squares down, and then we go 1 square like that, and then 2 squares like so, okay? And so basically, what that just means is we're losing displacement after every time we come up and down, okay? So we can come down like this, come up like this, come down like this, come down like this, like so, okay? And as you can see, we kind of form this curved shape like so, like that. That's kind of what they want to see, all right? There we go. J moves to a new swing that has a tire hanging vertically on a single chain. The system is a conical pendulum. J travels at 2.61 meters per second around a circle of radius 0.411 meters. The total mass of J in the swing is 70 kgs again. Calculate the tension in the chain supporting the swing and the angle of the chain from the vertical. So if we were to just draw this out, all right, we know that we would have a weight force coming down, okay? There is a tension force through this chain, okay? And we obviously have an FC towards the center of the circle, which is making us travel in a conical pendulum, okay? And so therefore we can make a vector triangle of this. We can have our weight force coming down, our tension force like so, and we'd have our FC like that, all right? So this is our weight force, our tension force, and this is our FC, which again is our net force, okay? We know our weight force is equal to mg, and we also know our mass is 70 kgs times 9.81, which is our g value. And this gives a weight force of 686.7 newtons. There we go. We can also calculate our FC, as our FC is mv squared all over r. We are obviously given our mass, we are given our velocity as 2.61, and we are also given our radius of 0.411. So we can simply plug in those numbers, 70 times our velocity, which is 2.61 squared all over 0.411. And this gives a centripetal force of 1,160.21 newtons. All right. Now, right over here, we have a right angled triangle. And so therefore, as we just found our weight force and our centripetal force, we can use our Pythagoras to calculate our tension force. And so therefore, our tension force is equal to square root 686.7 squared plus 1,160.21 squared, and this gives a tension force of 1,348.2 newtons. There we go. Now that we have all that information, this is the angle from the vertical, so we can calculate that angle. Therefore, we have our theta is equal to inverse tan 1160.21 all over 686.7, and this gives an angle of 59.34 degrees. There we go. Now, for calculating this angle, I highly recommend you don't use the tension force that you just calculated to find this angle. I suggest you use the weight force and the FC, which was what I did. The reason for that is because we are given all our values to find the weight force and the FC, right? We're given our mass, we're given our velocity, and we're given our radius, and so it's pretty hard to get those wrong. However, it's more difficult to mess up the tension force, and so therefore if you mess up the tension force and you calculate the angle using that, you could also get the angle wrong. Also, this is equal to 1.04 radians, so if your calculator was still in radians from the previous question, then if you got that answer, you're also correct. And we're done. See you.